So there's dust headers. There are two processes can create dust headers. One is human exploration activities, just like the previous talk as mentioned. You can see on the left, that's Jack Smith's spacesuit. It's fully covered by dust when he was doing a field investigation. And also on the right, so previous speaker has shown that there's dust kicked up by rovers. And in addition to that, there's also natural process called electrostatic dust charging and lofting. Can also create dust hazard. On the left shows random glow, and that can kick up a lot of dust. And also the LEAM instrument also measured the low speed dust across the terminator, which indicates there's also naturally lofted dust. So we have dust issue. What do? We have to mitigate dust. So here's a quick review about current dust mitigation technologies. There's a fluidal method using compressed gas or liquids to wash dust, or you can use a mechanical method like brush or vibration to shake dust off. And currently there's electrostatic dust shield, which is a popular one of the leading technologies. So it's basically apply the high voltage, oscillating high voltage on embedded electrodes on the protected surface to oscillate the charged dust and remove dust. Also, you can use passive method, like you can do surface modification to reduce the adhesion on the surface between surface and dust. But all these technologies have pros cons, and so the discipline is something like some methods that are low efficient, and some technologies are high efficient but more complex, and some requires you bring supplies from Earth. So it's some issues. So we definitely need new technologies to fill the gap. Well, thanks again. The previous speaker has shown this image and on the left, but this one is better. It's a movie. You can see when we blast dust on glass surface, and they jump off like crazy. So we can zap away dust by expose them to an electron beam. And the physics behind this is we learned from our study for natural electrostatic charging and lofting. And on the right, it shows how it works. So between dust grains, there are macrocavities. So what happens is electron beam penetrate and generate secondary electrons, and secondary electrons can charge up the macrocavities. And then the charged particles, they repel each other to eject off the surface. So that's how it works. So in 2020, we did our first experiment to demonstrate the feasibility and efficiency of this technology, and using the electron beam. So on the left, it shows the experimental setup. So we have a beam from the top shooting down to the surface with dust covered, and at the bottom shows before after. This is lunar simulant on glass sample. You can clearly see there's a cleaning process. So we try to understand, what's the best, what's optimized parameters for the beam, including the beam energy and the beam current density. So on the right, it shows beam current density. It shows cleanness as a function of time at different current density. And on the right, it shows cleaning as a function of time at different energy. So what we found is you need the energy, around 200 eV. And the current density is larger than 1.5 to 3 microamp per square centimeter. So we can clean the partially covered surface to up to 75% within a time scale like 1 to 2 minutes. We tested on the glass and spacesuit samples. So then follow-up experiment in 2021, we think, okay, so the idea is we need to expose more macrocavities to the beam to increase the cleaning efficiency. So on the left, you see this is the modified patch charge model. So you have beam from different angles because macrocavities are organized in a random way. So you need to have a beam coming into different angles to increase the exposure of the cavities to expel dust. So the bottom shows the same setup. The difference is this time we rotate the sample surface. Well, instead of rotating the beam source, it's easier to rotate the surface, but we made sure dust won't fall off by gravity. So that way we can change the relative, we can vary the beam angles to dust. So we did 3 tests on glass, spacesuit, and the PV panel. So there's 2 steps. First step, we just did fixed surface, so just like our first experiment. And then once the cleaning process stops, we start rotating the sample. You can see there's a bump increase that indicates additional rotation can increase the cleaning efficiency by 10 to 25%. So that's pretty significant. So for glass and spacesuit, we got 83 to 92% cleanliness. And for PV panel, for some reason, it's a little bit harder to clean them. So we only got 50 to 63%. So maybe that surface is more adhesive to dust. So here this is new results. So, the idea is to vary the beam angles, but the rotating surface or beam angles sometimes may be inconvenient on the lunar surface. So we try to find a different configuration to implement the same idea. So what you can do is you can have multiple beams at fixed angles, but they're fixed at different angles, and they can all point to the target surface.
3 minutes.
All right, thanks. And so that can give you multiple beam exposure angles on dust. So we did a test on a larger variety of samples. On the top, you see the PV panel before and after, and the bottom is the spacesuit, and you can see the whole cleaning process. And by visual look, virtually all gone. But if you look at more carefully with the camera, we got about still 90% cleanliness. There's still 10% dust on the surface. Again, the PV panel shows about the same cleaning efficiency, about 60%. Then here we did 3 samples: glass, thermal blanket, and Kapton. You can see they all reach about 80 to 90%, so they're pretty good on those stuff. Also, we tested aluminum and anodized aluminum. So aluminum is hard to clean them. And on the right, it shows the plot shows the red curves for aluminum. So we only reach about like 30 to 40%. And the reason we believe is that because aluminum is a conductor, so charged dust will generate the image charge. And the image between image charge and the charged dust, there's an attractive what we call mirror force. So that will hold dust on the surface, make them harder to be ejected. But once we switch to anodized aluminum, which had the thick oxide layer, you can see the cleaning efficiency bump up to 90%, pretty high. So, so in conclusion, we think this is a new technology to help clean dust in a better way, and we tested different configurations depends on the requirements for dust cleaning. You can choose which one is the best, but to give you the basic idea, we can clean dust to up to 90% within like 2 or 3 minutes. All right, I will stop here and take questions.
Perfect. I think we have time for one quick question. And always remember, virtual attendees, you can punch stuff in the chat and we will read it out loud.
Could I ask a question about your phase 2 study? Your graphs looked like they showed that it was harder to remove the thin layer of dust versus the thick layer. Could you comment on why that you think that was the case?
So yes, the thin layer is we covered the surface like not 100%. When you cover 100%, there are multiple layers, and the multiple layers, I think because of gravity, so the surface is more packed, so that's making them harder to be clean. I hope on the lunar surface it's easier because there's only 1/6 gravity.